Afternoon of Soergel bimodules, as Ben would have said. So the main idea that I want to sell today is, so what we want to study is if you have some kind of Hecke algebra for some Coxeter group. And what you usually want to study is, well, let's say it's reps. So you want to classify, or at least parameterize the simples. This is a very classical question. And so what we are basically asking is the categorification of this. So this will be mostly in the next talk. So there's a category, the Hecke category, the Soergel bimodule category, whatever you want to call it. And we are basically asking the same question. So what are the simplest possible two representations of this category? So the question would be, the big question, can we classify so the analog of this kind of simple two representations of the Soergel category, of Soergel bimodules, Hecke category, whatever you want to call it. Okay. So this is a big question we want to answer, and it turns out that we have an almost complete answer or a complete answer, depends a little bit whom you ask from our group. So those are all my collaborators, and that's what we want to explain today. So kind of, morally speaking, a complete answer to this question, the classification of all simple modules or simple two representations of Soergel bimodules. And being the first speaker of a series of two talks, I have the great pleasure to don't tell you anything new. I'm basically giving a 60-minute introductory talk about the main ideas behind, in the end, the proof of the full classification of the two simples of Soergel bimodules. So kind of the newest result I'm going to mention is about 10 years old, and then you will see the new results in the next talk. But there are two takeaway messages, which are with my subtitle "or." So I want to sell the following idea. I want to say that we have something that I would call semi-group-like things, and on the other hand, we will have group-like objects or group-like categories, whatever. And on this side, what you would put here is, of course, Soergel bimodules, S-BIM. But also you could put something like Tukac-Moody categories or whatever. So some very non-semi-simple things. And on the group-like side, I will put something like, which is really group-like, so fusion categories. I'm going to, if you've never heard about fusion categories, I'm going to explain what they are. But you can think about something like rep of a finite group, or G-graded vector spaces. G is always a finite group. So this is semi-simple. And this usually is very complicated and non-semi-simple. Let's say just non-semi-simple. And what you kind of want to have is kind of a magical procedure. It goes from here to here, and then you classify everything on this side, which is pretty easy. It's group-like, and then you get a full classification on this side. Kind of the story I want to sell is that there's a group-like part and there's a semi-group-like part. Okay, to get started, let's start with semi-groups. Right? So here's my a really classical theorem of the theory of semi-groups. It goes back to people like Clifford and Green about 80 years ago or 70 years ago, something like that. And the main question is the following. So we have a semi-group, and the semi-group, well, think about those examples. So my favorite example, of course, the natural numbers is a semi-group. Semi-group, by the way, just means a group without inverses, right? Or a monoid. Another example, for instance, the first thing you would encounter is instead of looking at the symmetric group, you just look at all n-homomorphisms of the set 1 to n. That's what people call the transformation semigroup. But of course, groups are semigroups, right? But basically everything that is kind of multiplicative closed sets, subsets of matrices, everything that has some kind of associativity constraint. Right, so the picture to keep in mind is when I click on this funny link here, it's the following. Sorry?
So do you want unit in your semigroup?
So there's a slight difference between semigroups and monoids. And to any semigroup which doesn't have an identity, you can always adjoin it. And I'm not going to, so I'm usually going to talk about monoids. There's not a big difference between semigroups and monoids. Okay, you can always embed any semigroup into a monoid, and the monoid has just one more thing, and it's just a unit. Okay. What I just said is, so I stole this picture from Wikipedia, of course, and well, semigroups are basically, okay, formally speaking, something like a category isn't a semigroup, right? It has multiple objects, but in some sense it always also fits into this framework. Semigroup just means what I want is associativity, and that's basically it. Right. So, and usually I like to ask the organizers to guess how many semigroups there are, because there are quite a lot. So, for instance, all of you know that you have 5 groups of order 8, and there are about 2 million semigroups of order 8. So kind of the slogan is everything is a semigroup and almost nothing is a group. And you just play around a little bit, and always the easiest example. So our good old friend T2 already, so the transformation semigroup, T2 is already not semi-simple. And I'm working over the complex numbers, so it even gets worse in characteristic P. Already over the complex numbers, this is not semi-simple. And when you go to something like T5, I think it's the first one. This is already of wild representation type, so it's hopeless to classify in decomposables. So this looks pretty much like a, so now you stand here, you know basically everything is a semigroup. There's zillions of semigroups. They're not semi-simple, they basically tend to be wild. So it really looks like this wants to be an absolutely hopeless problem. You can say nothing about the representation theory of semigroups. But it turns out that there were some very smart people like Green, and they tell us actually we can say quite a lot about the representation theory of semigroups. So what do? You define cells. Cells in this context are defined as follows. So you have left cells, right cells, and two-sided cells. And if you understand one of them, you understand all of them. The idea is you just say x, and x is an element of my semigroup, is left lower than y if you can find a z such that y can be factored using z from the left, right? Same from the right, same left, right. And the equivalence classes, as usual, under this order relation. So this gives you a partial ordering. And you take equivalence classes under this order relation. And that's what you call cells. The crucial example I want to keep you in mind is whenever you have a group, your cells are pretty boring. Okay. I've written it here, but I want to do it live anyway. So whenever you have a group, right, a group element G, I claim that it's always left, whatever, left, right, lower than everything else. So what can we do? We can just take whatever, which is my order, you can just take y, sorry. You can just take x, z to be y, g inverse, and of course then you get y, g inverse, g equals x. So every group element is always in the bottom cell, in the bottom equivalence class. Okay, so for groups, the group will cluster itself in the bottom cell. But for semigroups, interesting things can happen. So here's my example. So what people like to do in this business is they like to draw those diagrams. These are called egg box diagrams or egg box shape diagrams, and it just works like this. So the big rectangles, this one, this one and the bottom one. These are the two-sided cells. They are ordered in my picture from top to bottom. So the lowest one is at the top. The biggest one is at the bottom. My convention is somehow that I want to think of it like a tower, and if the big one would be at the top, then it would kind of topple over, right? So lowest one is at the top, and biggest one is at the bottom.
Lowest and biggest are not the same category of words.
Whatever. If your co-author disagrees with you, it's always bad. Anyway, the point is, here you can, so this is a transformation semigroup T3, okay, 3 elements, all anamorphisms of the set 1 to 3 in one line notation. So this just means 1 goes to 1, 2 goes to 2, 3 goes to 2, right? You should recognize that this guy here at the top is the is S3, the symmetric group. And then you get here in the middle certain elements, and at the bottom you get kind of the worst case elements, if you want. Okay, this picture, as I said, the big rectangles are the two-sided cells, the two-sided ideals. The columns are the left cells, the left ideals. The rows are the right cells, the right ideals. And those little rectangles are called H cells. This is an intersection of a left and a right cell. And now comes this amazing fact due to Green, mostly due to Green, that you can see it here. So each of my small h's contains either an idempotent or no idempotent, right? So it's idempotent separation. So the big ones are idempotents. This is of course an idempotent. If you apply this to itself, it's of course an idempotent. Some might not contain an idempotent. Right? And he also tells you, Green also tells you that each, so you kind of don't care about those. You always look for idempotents, okay? So each one of them is actually a maximal subgroup in your semigroup, right? In this case, it's a symmetric group, S3. For those, you can just check that this will be the identity in S2, and this will be the non-trivial element in S2 if you just consider those two. Same for all other purple ones. And here is just S1. This is again true in complete generality. And he also tells you that each simple, and that's what we are up for, of our semigroup has a maximal two-sided cell such that the idempotent in this cell doesn't annihilate your simple module. So you get an ordering on the simple modules. And this maximal two-sided cell is usually called the apex. Okay, summarized, the semigroup kind of breaks itself into those H cells, and those H cells are maximal subgroups of your semigroup. Okay, and then comes this amazing theorem of Green, who just tells you, actually there's a one-to-one correspondence between the simples of my non-semi-simple semigroup and the simples of those maximal subgroups. Okay? And this is pretty amazing. I mean, this is really, really pretty amazing. It holds in complete generality for semigroups, for those 2 billion semigroups out there. And it reduces, well, let's work over C, then groups are semi-simple, representation theory is semi-simple. One of the most beautiful theories out there. And this very wild representation theory of semigroups, and if you only care for parameterizing the simples, the only thing you need to do is to look at those H cells and to check what kind of group you see. Okay, in this example, let's just do it together. So here we have S3, S2, S1. Right? You can choose freely, you can choose this one, it doesn't matter. All of them will be Morita equivalent, whatever you see, all groups. So we just choose for each two-sided cell, you choose an H. Okay, here's nothing to choose, but whatever. You see S3, S2, S1. And then the theorem tells us that actually T3 has 6 associated simples. 3 which are survive, which are 3 of them are killed by this cell, so they have apex this one. 2 further ones are killed by this cell, so they have apex this one. And 1 that survives everything, so where those guys don't act as 0. Okay, this is a very, very fascinating theorem. And I want to keep it on the board for a second. Really, really nice. And this is kind of a general philosophy in representation theory, if you have seen this before. So all those notions of quasi-hereditary algebras and Castalistic cells and cellular algebras in the end go back to this theorem, which is stressing my luck a little bit too much, but both, for instance, with cellular algebras we associate someone like Gaslera, and with Castalistic cells, of course, Lusztig, and both of them were actually postdocs with Green in Warwick at one point. So this is kind of really where it comes from. Pretty easy, of course. One last thing before I go on. So usually you want to have a nice anti-involution, because as you can see, my cells are not are rectangles but not squares. So life gets much easier if your cells are squares and not rectangles. So from now on, everything you will see will have some nice involution, and everything will be square-shaped, which makes life much, much easier. Okay, summarized semigroups, kind of, you can, well, what I've raised here, you can kind of, on the semigroup level, you can really go from here to here. And what we want to sell is kind of on the categorical level, it will still work. You can still go from here to here. But first, let's analyze a little bit the problems which arise when you go on. So this is a categorification conference, so think categorical. So what I write upstairs is just, okay, I have some algebra. For later purposes, I want to work over that ground ring because I want to have some Hecke algebras, but whatever. You fix a basis, and you play the same game, right? You just say x is left lower than y if there exists a z such that y appears in an expression. So this one will, you can write it in terms of your basis, and y appears as with non-trivial coefficient. Categorically speaking, you have two indecomposable objects, you tensor them together, and you look whether y appears as a direct summand of the tensor product. But you just play the same game, left cells, right cells, two-sided cells. Equivalence classes, whatever. The group-like example, if you take something like the group ring, maybe my coefficients are wrong, so just the group ring with integral coefficients, and you choose the group element basis, okay, as this choice of a basis, then the cell theory will be boring exactly by the same argument I made before. Everything will cluster in one cell. This is a group-like case. Okay? Everything will just be one fat cell. But otherwise, it's just the same as Green did, but just in linear. It turns out it doesn't work. It turns out it doesn't work all that nice. Let me do an example. So this is the Kazhdan Lusztig. So I'm going to use Hecke algebras. So I'm going to use the Hecke algebra of type B2 here as my running example. And I want to choose the Kazhdan Lusztig basis because I'm already, of course, thinking about Soergel bimodules. And then you do this calculation. Oh, just that we are on the same page. Let me click on the link. Okay. So whenever you have a Coxeter group, it will look like this. This is type B2. You have a braid relation. You have a quadratic relation. You can always associate the Hecke algebra, which will look like this. The braid relation stays unchanged. And you throw in some quadratic relation. And the point is you will have exactly the same number of basis elements as you have elements in your Weil group, in your Coxeter group. And you also have this nice Kazhdan Lusztig basis, which I don't want to write down because kind of point of the game is this basis is really nice. It exists, but you don't write it down. You really don't want to. But there is a Kazhdan Lusztig basis. That's the only thing you need to know. And it's the base change between this one and this one is governed by what is usually called those Kazhdan Lusztig polynomials. And in my notation, for instance, if you take this one and you square it, right, you can explicitly use those relations, and you will see that it squares to, it is a pseudo-idempotent, right? It's 1 plus v squared times itself. But it's kind of positively graded, right? It has a 1 and something higher. Okay, but just to be on the same page. So this is the type B example. In general, I'll just do it in general. Okay, and now we write down the cells, or you ask a computer to do it, or whatever, and it will look like this. I just identified my basis elements with the elements in my B2 Weil group, and it will have some the unit will be at the top, and in the middle, the longest element will be at the bottom, and in the middle we will see this pattern. In particular, we'll have an H cell of size 2 here. Okay. And then you try to analyze what's going on. You try to mimic the approach of Green, and you actually realize that this doesn't quite work. So the philosophy is the following. Let me just mention it again. Left cells are like left modules. Right cells are like right modules. Two-sided cells are like bimodules. And those H cells are like subalgebras. To be precise, if you just take the elements in your basis supported on the H cell, then they form a subalgebra up to bigger cells. You just kill the bigger guys, you don't care, but otherwise you get a subalgebra. However, it turns out that they in general do not parameterize the simples, as in the nice semigroup picture. This really depends on your choice of the basis. And moreover, you lose kind of the property of having idempotents. They usually tend to be quasi-idempotents, as I just did for this example, right? I just wrote it down, that CS squared is 1 plus V times CS. So it's not an idempotent, it's a quasi-idempotent, which you're of course very happy about if you just work over some field, then you can just divide by this number and you're very happy. But we're doing categorification or representation theory, characteristic P, whatever you want. So we can't divide by those numbers, right? E squared equals 2 times E is really bad in characteristic 2, for instance. So this is bad from some point of view. And SH tends to be not even group-like. It's really horrible. Let me just show it to you in order to make sure that this is really not easy in general. Obviously, I haven't done this calculation myself. Obviously, I ask a computer to do it. But this is the multiplication table of the Castalistic basis elements in type B2. And as you can see, so here are my H cells. And it's a nice subalgebra. So CS times CS is a multiple of CS. CST is a multiple of CST. And if you kill the bigger guy, then actually you have a nice subalgebra. But it's kind of complicated what you get. I mean, this is B2, and you still get some funny quantum numbers that you can't divide by, and so forth. So this is really not nice. So kind of the whole idea is now, what can we do? So let's assume we really love Green's theory. So you're like me, and you like semigroups and the theory of Green's. So actually, what on earth can we do to recover some H cell theorem? Right? We want to reduce the group-like picture to the semi-group-like picture, which was here. The other way around, of course. We want to reduce the semi-group-like picture to the group-like picture. So what on earth can we do? Okay. And it turns out, and that's what Vanessa is going to talk about, that there was this choice of basis, and of course, on the categorified level, there is no choice of basis, right? I never was really aware of it because I started kind of this whole theory working on Tukac-Woody algebras, and for Tukac-Woody algebras, there's just a standard choice of a basis, a canonical basis, so there's kind of a standard choice of a categorification. But different choices of basis should have different categorifications upstairs. But if you already choose your category, like I like Soergel bimodules, then there is no problem about choosing a basis. It's just the equivalent. You just take the equivalence class of indecomposables on the Grothendieck curve. And it turns out that in this case, very, very surprisingly, the H cell theorem actually holds in some sense. We will see it. And the problem is that SH, so Soergel bimodules, for instance, is still not group-like. And that's kind of what I want to solve. Okay? So believe me for a second that this problem that you don't really parameterize the simples, it will vanish in thin air if you look at the categorified level. But this doesn't. And I'm going to explain why there is no reason that this does hold. Okay, so this vanishes, and this is still something we need to do. So let me just summarize what I just said. So in a few minutes, we will see the whole categorified picture. But now let me explain actually how you can make this guy group-like, because it's a really nice general philosophy due to Lusztig. Okay. So let's do an example calculation. And of course, my favorite example is type B2. As I said, this is type B2. Number of elements is 8, number of cells is 3. We have seen it before. This is the order. Those are the cells. And the only thing you need to really remember, it doesn't really matter whether this is S or SDS. The only thing you need to remember are the size of the cells. So 2, 2, 1, 1, 1. Okay, just some notation. Okay. So for example, type B2. And then you start doing some calculations. And as I said, I'm super lazy, so I have a computer program to do it. Obviously, I could have done this myself, but still, I'm so lazy that I even did this calculation with the computer. But for the computer, it's pretty easy. You just can compute the products of Kazhdan Lusztig basis elements, and you realize that there's a nice pattern. Whenever you multiply them, there is a leading coefficient, which need not to be 1, but at least there is a leading coefficient, and there are bigger powers. Or there is a leading coefficient, and there are bigger powers or higher cells. And higher cells always die. We always kill them. Okay? Just do this calculation in type B2. This is how it looks like. Same for the last cell. And actually, what's going on here is a general statement due to Lusztig. And in this setup, maybe also proven by Soergel, Elias, and Williamson in some sense. So for each Coxeter group, there's this well-defined A value, which is just a numerical value that you associate to each group element. So just a function from W to the positive numbers. And this is kind of the maximal power you'll see. Okay? And the statement is you can renormalize the classical Kazhdan Lusztig basis, which I've already done implicitly here. So the C's are renormalization of the classical Kazhdan Lusztig basis, such that actually this is positively graded. Meaning the only things you see are V's, or constant terms, and bigger things you would kill anyway. Let me do a big example before I go on, but this is pretty good. I'm going to come back to this in a second. So remember, Kazhdan Lusztig is positively graded. Okay, so if you go to type B6, you don't really want to do calculations by hand anymore. So the cell order gets pretty tricky. It's pretty huge. The whole group has something like 46,000 elements. Here's a very fat cell with 14,000 elements. There's a cell in the middle, cell number 12. And you can write down the A value explicitly. You can just compute it by computing certain Kazhdan Lusztig polynomials. It's not so hard. Well, by hand, of course, it is. But in practice, it's not. And those cells get pretty complicated. So cell 12, for instance, looks like this. I told you just look at the numbers, forget the elements. I mean, writing down those elements would be horrible. But in principle, it just looks like this. So this just means this is a 25 by 5 matrix with only entries 5. And what we want, just to remind you, you have this huge cell, and there should be some symbols associated to the corresponding category, which is supported on this huge cell, which has 14,500 indecomposable elements. And we want the trick to reduce it to just this H cell, which has 4 indecomposable elements. That's kind of the big step we want to do. We're not there yet. We will go there. Just to let you know that this is really a huge reduction in the end. Right? So the H cell theorem is really, really amazing. Anyway, this is pretty scary. And it gets worse. I mean, this is type B6, right? B6 is. And this is how those calculations usually look like. Just to be completely explicit, this is my convention. Here's the elements, so S1, S3, S2, and so on. I just choose this element, and I just compute, or let my computer program compute the Kazhdan Lusztig basis elements multiplied with each other. And you get such a result. I mean, this is terrible. Those coefficients get as big as you want if you go to higher groups. I mean, this is just terrible. Right? Whatever. Okay, but then you exactly play the trick I just said. I mean, it's positively graded. So the first thing is, notice the following. It doesn't want to be positively graded here, right? But magic happens. This actually. So I want to define a new basis which I call A. Okay, and the multiplication in A works as follows. First, you see that this actually lives in a bigger cell. So we were a little bit in trouble here because this is not positively graded, but it lives in a bigger cell. It dies. It just dies, okay? Gone. And now it's positively graded. So what can you do? Well, it's positively graded. There's one value which you, right? I'm working, this is really, really important. I'm working over this ring. Right? This is where my Hecke algebra is defined. There are exactly two values. This is, of course, built to be such that I can specialize to everything I want. I can specialize my characteristic, I can specialize my V. But there are exactly two values which you can't specialize to, right? This is V equals 0 or V equals infinity dually. And this is exactly what I can do because this is positively graded. So I can take the limit V to 0 in this case. I can just throw away everything. And this is my new multiplication. So this horrible multiplication turns, oops, sorry, this one turns into this simple multiplication. So there's something really going on here. And let me explain what it is. So now you use this trick. This is positively graded. There's one value, as I said. Now you can just evaluate your the appearing polynomials at 0. Take some kind of asymptotic limit. And that's exactly what you do. This idea goes back to Lusztig. And this is exactly how you define the so-called asymptotic algebra, the asymptotic limit. It's just as a module, as a basis, it's just use different symbols for the same beast, just the same basis elements. Okay? But the structure constants are much easier. The structure constants are just the evaluation of the usual Castalistic structure constants at this value 0 because it's positively graded. So why not evaluate at 0? And this really, really is, I want to think that this is some kind of crystal of a Hecke algebra, despite the fact that this is much older than the notion of crystals, right? So a crystal is, so this is really a crystal limit for the Hecke algebra. You take a value which you actually can't really, you evaluate at a point which you can't really do. But you can because it's positively graded. Okay? So you have this asymptotic Hecke algebra, so which just comes from here by throwing away, okay, bigger friends, right? Just kick them out and just evaluate your appearing coefficients at 0. It's called the asymptotic limit. Originally, it's called the asymptotic limit because Lusztig uses actually this value, and then everything would be negatively graded. But I kind of like to prefer the positive grade setup. And this is the example now. So if you do now the calculation, so this was the big table from before. If you do now the calculation, so here are the H cells. And I mean, this is really, really easy, right? Here's AS times AS is AS. AS, in this case, is the unit of your subgroup. And this is just Z mod 2. The thing you see here is just Z mod 2. Instead of something complicated with funny quantum numbers floating all over the place. Okay? And this is really then the main fact. Actually, these are really group-like objects. So those fit in here. The decategorification of fusion categories, I will come to fusion categories in a second. But the main fact is now that AH, I will write it down here. So A0, 0 is my value. W is multi. Well, the multi is just referring to that the unit is not necessarily indecomposable. It's a multi-fusion, meaning it's very, very semi-simple. I'm coming back to this in a second. Okay. This is part 1. So this is really simple. It comes from. Well, let me just write it down. This is really simple. Okay.
We are talking about finite type algebras, right?
No, not for this theorem. This holds in complete generality for every Coxeter group.
For that,
Oh, for fusion, yes, because, yeah, that's correct. Okay, thanks. So the fusion, as we're going to see, actually refers to you have a finite number of indecomposables. Finite. But otherwise, it's a general statement for any Coxeter group. Thank you very much. So this is really easy. And the very surprising fact is actually, due to Lusztig, is the following. I mean the following amazing theorem, that if you allow to invert all those numbers. So you really work over a field. You're allowed to invert all those numbers. Okay? Then actually the asymptotic algebra is isomorphic to the Hecke algebra itself. So over asymptotic is isomorphic to Hecke. It looks like you throw away everything, but it's isomorphic. So everything is controlled by the leading coefficient of the Castalistic structure constants. And in general, you get even an embedding. The only thing you need to do is you need to invert those funny scalars which turn up. So those Castalistic structure constants. And it is an amazing statement. It really feels like you have thrown away everything. Remember this type B6 calculation. It just shrinks to basically something trivial. It's equivalent. So they are isomorphic. This is pretty good. This is pretty nice theorem. Due to Lusztig. In particular, of course, so by the way, this is, if you want to think about it in over the field, then this is an explicit Wedderburn decomposition. So this is an explicit isomorphism. And this is an explicit Wedderburn decomposition of this beast, which is, of course, semi-simple over this ground field. Okay, so this is explicit. And of course, then the consequence is that you can order the simples of this one by cells, because as you can see upstairs, this one is defined as a direct sum of different algebras supported on two-sided cells. So you kind of get, again, the same statement. The simples, so you can order them into APCs, and the simples with a certain apex here and one-to-one correspondence with the simples of this much easier guy. And this is what we want to categorify. And this is actually what we can categorify in almost all cases. Okay. To wrap up, and then going to the categorified picture, then you might wonder, actually, can you compute those guys explicitly? And you can. So in almost all cases, so now I'm going to the finite Coxeter group case. In almost all cases, and this is crucial, in almost all cases, this is super simple, right? We have seen it, it was Z mod 2, and this is not a coincidence, it's almost always Z mod 2. So the elementary abelian group for some k, in almost all cases. The exceptions you see actually already showed up in Ivan's talk, so in type E 6, 7, and 8, and F4, so the exceptional types, and G2 is different, you actually also see S1, S2, S3, S4, and S5 turning up.
We see S3 for G2 as well.
Sorry?
As far as I remember, you have S3 for G2 as well. Subregular in
Say it again.
S3 also appears in G2, I guess. No?
S3 doesn't appear in the classical types.
No, but it appears in G2.
Yes, S3 appears for E6 and E8.
And G2, no?
Yes. We can discuss it later, but there is some finite list of exceptions. S3 appears for E6 and E8. I will come back to this in a second. Maybe that's why it's confusing. It doesn't appear as a group ring, but it appears as the Grothendieck group of the representation category of S3. Okay, but anyway, up to some very finite list of exceptions, something like 15 in total, whatever. This is a general statement. It's almost always an elementary abelian group, which is much easier than everything you can do using Castalistic combinatorics. Okay, I will skip this due to time reasons. You could play some games here with the corresponding APCs. In particular, in type A, for instance, this K here is always 1. So A0 is always Z. And actually, you get a complete classification of the simples by APs, by two-sided cells, which for the experts is because the Castalistic basis is cellular in this case. And outside of type A, it's not. But in type A, it's really simple. And the asymptotic algebra is just the ground ring. Right? It can't be much easier. Okay. 20 minutes left. Not too bad, right? So let me summarize what we have learned before we go on. So there is this funny H-cell theorem for semigroups, and it's really amazing. It works pretty nice. It doesn't quite work if you work with algebras. It will, again, on the categorified level. But you can at least recover in the setup of being positively graded, like in the Castalistic setup, you can at least recover that the H cells are group-like. In a very strong sense, they are basically elementary abelian groups. Okay. Categorified picture will be almost the same, which is pretty nice. So there is this category of Soergel bimodules, and this is the only thing basically you need to know about it. I will do an example in type A1 in a second, but the statement is just there exists some Soergel bimodule category for each associated to each Coxeter group, such that the incomposable objects correspond to the elements of the Coxeter group, and the incomposable objects categorify exactly my little CVs. And the crucial ingredient is Soergel's hop formula, which tells you that everything is positively graded. So the graded dimensions between those basis elements is basically trivial. Right? Okay, so Soergel bimodules are positively graded. That's part 5. Let me give you an example. I don't want to define Soergel bimodules, but so if you have never seen Soergel bimodules before, this is a definition in type A1. So in type A1, you just do the following. So in type A1, which is of course this Coxeter diagram, not very interesting. So you take the geometric representation of it. You take the polynomial ring over C. So here I'm really working over C. So this positively graded business is false in finite characteristic if you want to work with Soergel bimodules in finite characteristic. But for now I don't want to. And the degree of X is 2. And your Weil group, which is very boring in this case, it's just S2, and it acts here by a sign. Sx is minus x. Okay, and then you can define those Soergel bimodules. In this case, the two incomposable ones will just be the polynomial ring itself and this guy. You tensor over the co-invariant algebra, the invariant algebra, which in this case is just Cx squared. We have those two bimodules, and well, those are the incomposable Soergel bimodules in your category. They categorify those two basis those two elements. So one categorifies 1, and the other one categorifies Cs, of course. And you can do play the same game with the co-invariant algebra, which was Soergel's original one. Right? So later we will see that we really want to do it. In this case, it's not a big difference. Just instead of putting the polynomial ring here, you put the co-invariant algebra, which is always finite dimensional if my W is a finite Coxeter group. And then kind of what will happen is that home spaces will be finite dimensional. It's something that we want later for the categorified picture. But this is how the Soergel bimodules will look like. Okay, note the following funny calculation. If you now multiply CS with CS, as a bimodule, you get this guy. In the middle, you cancel this one. This is a multiplicity space. So this is just CS plus CS. And this multiplicity space tells you actually the grading shifts. It's 1 and 2. So you actually get this equation, which should remind you that CS actually decategorifies 2 by CS. Okay, so this is kind of how it works. Okay. Soergel bimodules in a nutshell. In general, very complicated because they categorify Castalistic combinatorics. So don't try to do any calculations in something like type B6, except, of course. And the main idea is now that there is actually a multifusion category. I'm going to click on the link in a second, and then we're going to explain what the multifusion category is. And it's called the asymptotic category. And it categorifies the asymptotic algebra. So there is some indecomposable objects. I will give an explicit example in a second, and also the construction in a second. And this guy categorifies my asymptotic algebra. And the indecomposables, which are now simples, because this is a semi-simple category, actually recover those crystal limits. And actually, this is really the degree 0 part of the Soergel category. Okay. Let me explain to you why this is good. So let me explain to you what fusion categories are. Okay. So fusion categories have the following. So I will stay on this slide for a while. So don't worry that there's much to read. So fusion categories are, by definition, just monoidal, rigid, semi-simple is very crucial, and linear categories with finitely many objects. It's exactly what Ivan said before. So in this setup, I'm really using finite Coxeter groups. So finitely many simple objects. Okay, so rigid is this duality. Monoidal is categorification of a ring, right? Semi-simple is a crucial ingredient here, and the rest is just whatever. And they have they have two very, very nice properties, which is usually called in this game is called Ogneano rigidity, which is very, very, very strange from the viewpoint of categorification where I come from. It really says there's only a finite number of ways to categorify a simple a given interesting object, right? The number of multi-fusion categories up to equivalence, of course, with a given Grothendieck group is always finite. So there are only a finite number of categorifications of your favorite algebra in this semi-simple multi-fusion business. Same for module categories of your multi-fusion category. And this is extremely crucial because this is really, really wrong in general. There's a very, very, very tiny example. It's just a 4-dimensional algebra. It's called the Taft algebra. And if you take its module category, it will satisfy everything you will see later, except that it's semi-simple. And indeed, this very, very small modular category has just four indecomposable objects. It's not semi-simple. Has infinitely many modular categories. You can really twist everything with a one-parameter family of complex numbers, basically. So this is extremely crucial. So in this proof, which is really beautiful, I'm going to sketch it in a second. The semi-simplicity really comes crucially into the game, right? So if I want to think about my picture here, I have my group-like case here, and here everything is kind of finite, right? Number of categorifications are finite, number of modules are finite, and then I'm going to my semi-group case, and it tends to be pretty infinite, right? Even for simple examples, like the stuffed algebra, you already get a one-parameter family of modules. And kind of the big statement in the end is that the Soergel category isn't all that bad. The Soergel category, if our conjecture, we will see it, is correct, will have only finitely many associated two simple representations. Anyway, so let me give you some examples of fusion categories, or to be completely precise, let me give you the complete classification of fusion categories. There are only 4 types, and this will obviously be a complete classification. Also, you might be a little bit unhappy. So there are only 4 types of fusion categories, basically. Either you have Rep G. I'm going to discuss this example in a second. So finite dimensional representations of a finite group over the complex numbers. So this is definitely semi-simple. You have something like Vect G, so G-graded vector spaces, which is by definition semi-simple. You can have semi-simplifications of quantum groups, right? Like take tilting modules and kill the negligible modules. And this is basically the complete list. Everything else is called exotic, and it's, well, this is obviously a complete classification because I'm not going to tell you what exotic examples are, but morally speaking, there are only those 3 types. And this is also up to some exotic examples, exactly what you see turning up in Soergel bimodules, and the only thing you can do is you can twist the associativity constraint. So there will be twists of those guys, which if I have some time, I'm going to explain. Okay, but the pretty finite and pretty nice classification. If you take, I'm not going to tell you what exotic really means. Basically 3 kinds of examples. Okay. So, and this asymptotic algebra is one of those. That's kind of web. There you go. Kind of a message. Okay, let me do the example, and then let's wrap up. And yeah. So in type A1, you remember that we had those two bimodules. They are certainly positively graded, but you could check that this category they form this will be not semi-simple. And you just take degree 0 part, basically. So this guy gets much easier. Degree 0 part is just the complex numbers. And this guy gets also much easier. Degree 0 part is also just the complex numbers. So the asymptotic category is, again, much, much, much easier than the Soergel category itself. And again, I'd like to stress that the main theorem will be, up to some exceptions maybe, we are not completely sure, but the main theorem should be that this guy, which is much easier, completely controls, this lives here, completely controls the Soergel category when it comes to two representations, which lives on the other side. Okay. And the construction is pretty easy. You really just take the additive closure of your indecomposable Soergel modules and you kill everything you don't want. Okay. As I just did. And you can, of course, ask the same question on the categorified level, which I've just did here before. So on the categorified level, basically the same is true for almost all cases. This is actually just A0H is actually just vect of the elementary abelian group, or dually rep if you like, if you don't like vector of something. This is rep of the abelian elementary group. So this is as easy as it can be, right? This is basically a very trivial category. In type A, let me mention again, k will be 1. So, k will be 0, so this power will be 0. So in type A1, this one will always be vect, the vector spaces. This is probably, if you don't understand anything like me about two representation theory, you're kind of inclined to believe that vect should be easy. Right? Should have a very easy two representation theory. Okay, so this is my last slide, don't worry. So what we are what Vanessa is going to explain is really this relationship that I'm going to stress here. For now, it's just conjectural, but we basically have proved it in all cases. But anyway, the statement will be that the two representations in a very precise way of this category are controlled by the asymptotic limit. So why is this awesome? Well, for various reasons. First of all, of course, you really recover this reduction I wanted to have from before, like the groups versus the semi-groups. I'm going to click on this link in a second, and this is just much easier. So Soergel bimodules are not semi-simple. They're not even abelian. They're complicated, really complicated category, and they're completely controlled by something like rep z mod 2, which is pretty amazing. Of course, if you keep Ocneano rigidity in mind, then this really implies that you only have finitely many two equivalence classes of two simples. It's kind of a uniqueness of categorification statement. Because here, well, I will explain it in a second. You can basically just twist it. Moreover, this is just a statement. There are finitely many, but it's better. You get a complete classification because in this case, it's really easy, I'm going to do it in a second, to write down the complete list of two simples. Right? And of course, kind of, it should work for everything which is positively graded. The stuffed algebra example I made is not positively graded. It doesn't fall into this picture. Let me just end by giving you the complete classification of two simples of in this case, because it's pretty easy. Just to convince you that this is not something stupid, right? You first, let me just recall. First, you reduce it from this huge cell, which has 14,000 elements, to just this little part, which has 4 elements. And not just that this has only 4 simple elements, it's just something one of those, right? Rep z mod 2. In this case, it's for B2, it's a Klein foregroup. So it's C2. and rep or vect, whatever you want, of this guy. You reduce a basically horrible sounding problem to something pretty doable, and it really is pretty doable. Let me just run you through it. It's very easy. So rep G is my finite group. This is certainly a fusion category, right? I mean, I'm working over the complex numbers, complex representations, finite dimensional ones, semi-simple. It's a tensor category. Right? Here's a formula. You have a trivial representation. Everything's nice. And what is a two representation? A two representation would be, right? We have categorified representation theory. We are not looking at representations of G. No, we are looking at representations of the category of representations of G, which is just a two-functor to a suitable target category. In this case, it's a regular two representation, which is, in this case, super easy. It's just tensoring with your particular module. Okay. But you can do a little bit better. Note that all of these, of course, are decategorified to integral representations, right? I mean, by construction. You can do a little bit better. You can take a subgroup of your group, and of course, the representations of your subgroup is also a module category of your group, of rep G. How? Just by using the restriction functor. And this is again a two module. Another one. And it turns out that this is basically it, right? So before I go on and explain that you can slightly twist the statement, let me give you a good reason why this should be basically it. Okay? Why this representation theory of groups, of group-like objects should be so much easier. Okay. Whenever you have a group-like object where things are invertible, and you want to act on some category by endofunctors, whatever. Okay. When you decategorize this picture, you certainly get something positive. Okay. Certainly you get this guy acts by integral matrices. Okay. But now this is a group. So this is a group-like object. So elements are invertible. In particular, G inverse is also supposed to be an integral matrix. And they are not, just think about it for a second, there are not many matrices with only positive entries, whatever, which are invertible. This, for instance, isn't, because you just can't invert 2, right? They should be invertible over the natural numbers, which is a very strong restriction. So in one word, groups don't act interestingly on additive categories. Why not? Because there are not many invertible integral matrices. Semi-groups, however, can act interestingly on additive categories. It's kind of the whole philosophy here. Okay, so this should be basically it, because the only integral matrices here are permutation matrices, which you get by just fixing your subgroup. This is not quite true, it's almost true. This is it. What you can do is, always in this game, is you can twist everything. So you can twist the associator, and you can do it by some numerical data, which is called the Schur multiplier. Isn't so, well, it's really important, but I'm running out of time. So there is some numerical datum you can associate to it, and you can take projective representations, which are representations up to a well-behaved scalar, representations on a projective space, right? And you can form exactly the same procedure. You get a restriction functor, and those are also representations. And the not hard but not trivial theorem is that's it. So all two simples of a group are basically given by fixing a subgroup and one of those Schur multipliers, which are easy to compute. They're just some cohomology theory which you can easily compute and write down. So this is pretty easy. I just showed you this complete for general G. I just did this case of rep Z, what 2 to the k. Basically live. Okay, I haven't showed you how to prove it, but it's not so hard. Okay, so this is good. So if this works, then we are kind of done. If this works, we are kind of done. So let me, just my final slide. Let me come back to this example. So how does it work? Upstairs again, my folk theorem. So two representations of rep G are controlled by a subgroup and a cocycle. And the worst case you really see in classical wild types is that AH is rep S5, turns up in type E8. It's a huge cell with 40 million elements. Okay? And rep S5 has, of course, something like 7 indecomposable, 7 simple objects. So we reduce a problem of a category with 40 million indecomposable objects to a category with 7 simple objects. And you just play this game. You list the subgroups. I did it for you. Well, or let's say I checked Wikipedia, and Wikipedia does it for you. These are the subgroups. You just the Schur multipliers is always some finite abelian group. In almost all cases, it will be just assigned, so Z mod 2, and you can just list everything explicitly. And this is no magic. I just looked everything up in the internet, of course. This is a completely numerical problem. Right? So if everything works, and the main theorem will be yes, everything works. Basically, it will be yes, everything works. Then we've reduced a non-semi-simple problem for very complicated categories, Soergel bimodules of type E8 with 400 whatever million indecomposable objects, to a completely numerical problem computing certain subgroups and certain Schur multipliers of very, very easy groups. So the worst case you see is S4, 5. Okay. Up to some finite number of exceptions. And I'm over time, and this is never good, so thank you.